Okay, welcome back to my channel. I hope you are doing well. My name is Mr. Sandude. I come from the State University of DasTV. Today we are going to solve problem from the second law of thermodynamics. This is of very important. Let us jump together. We have a problem. A generator pump operating through a Carnot cycle draws heat from a cold reservoir at 12 degrees centigrade and transfers the heat to another reservoir at 75 degrees centigrade. The pump is governed by a reversible heat engine which extracts heat from hot bath at 920 degrees centigrade and releases it to 75 degrees centigrade. The heat engine expends a moderator that is used to absorb 45 kilowatts. If the generator pump extracts 25,000 joule per second from cold reservoir, then determine the power developed from the hot bath at 920 degrees centigrade and the power rejected to the higher temperature reservoir at 75 degrees centigrade. You have solution. We have that temperature 1, which is equal to 12 degrees centigrade, equivalent to 285 Kelvin. This is the temperature from which the generator pump extracts its heat content. Temperature 2 is equal to temperature 3, which is equal to 75 degrees centigrade, equivalent to 348 Kelvin. These two temperatures are equal. Temperature 2 is a temperature at which the generator pump pushes its heat content or transfers heat content so as to heat the space. I will have temperature 3, which is a temperature or space at which the heat engine releases its heat content from the hot bath. Also, we have temperature 4. This is a temperature from which the heat engine absorbs its heat content to transfer into the temperature 3. We have Q4. This is a power. Actually, the power, which is the NH per second absorbed by the heat engine from T4, from the region with temperature 4. Also, we have Q1. This also is a power, heat NH per second, that is extracted by generator pump from reservoir, cold reservoir, to a space at which it's desired to heat up. Our desired output of our generator is to heat the region at temperature T2. So let us see how can we find the power developed from the hot bath at this temperature and the power rejected to the higher temperature reservoir at 75. This here is our given data. I will have symbolized the HP as the heat or generator pump and the HE refer to the heat engine which driving the heat, the generator pump or heat pump. Here we have a diagram to refer. We are going to refer this diagram, and later we'll see how this system, a combination system, these two engines work. Let us start with To determine the power W2 developed from the hot bus T4, we follow some steps. Efficiency of heat engine, which is equal to W2 into Q4. W2, this is the output of heat engine. Heat engine absorb heat from temperature 4 and release this heat into temperature 3. So it's a heat exchange between this region and this region. But this is a power output beyond this heat exchange. So the power output over Q4 we call the efficiency, and which is equal to Q4 minus Q3 over Q4. Also in terms of temperature we have T4 minus T3 over T4, and then once you substitute here you get 0.708. This is the efficiency of a heat engine. Yes, from this value we can find W2. When you rewrite the formula, we can find W2 as a multiplication of efficiency and Q4, which is equal to 31.9 kilowatt. So this value is the required power developed by the heat engine. Okay, now we're going to see how these two engines work. The process starts at this point. A heat engine absorbs heat from this space and release to this space. As you can see here, the first step is after the first step we have second step. Over here the heat is released to this space, but also there is a work output over here. You can see like that. From this stage we come to the W1. This is a power received by a heat pump, as you can see here. Yes, after receiving this, now heat pump can absorb heat from the cold reservoir and reject the heated space to this space, to the hot reservoir. As you can see, this is the next stage. You can see there. Yes, and the last step or process is over here, where the desired output is achieved. As you can see, like that. So after that, we are going to see the next part of our question. Yes, now the power Q2 rejected by a generator pump to the higher temperature reservoir can be determined as follows. We have the coefficient of performance, COP, of generator pump or heat pump. COP is given as a desired heat output into heat input. As we have seen, the desired output of the heat pump is Q2 at the last process over W1. W1 is the amount of heat received from the heat engine, received by heat pump from heat engine, and therefore can find the coefficient of performance by using these two heat. This can be written as Q2 over Q2 minus Q1, which is equal to T2 over T2 minus T1 in terms of temperature. And once you substitute, you get 5.52. So this is a coefficient of performance. So now from this value, we are going to find the Q2, which is a product of COP times Q2 minus Q1, which implies to this expression, and if you multiply this, then you divide, you get 30.5 kilowatt. So this is the power rejected by a generator pump to the higher temperature reservoir. So this is our final answer. I hope you enjoyed the video. Thank you.